The upcoming version of Starship will be equipped with Raptor 3, an impressive piece of propulsion technology that looks almost too sleek to be real. It's the latest evolution of SpaceX's advanced methane-fueled engine, and it's already pushing the limits of modern rocket engineering. But here's the twist. SpaceX isn't stopping there behind the scenes. The company is already preparing the next major upgrade, known as Raptor 4. So how do you even surpass Raptor 3? Well, here's what Elon Musk has revealed about SpaceX's next-generation engine architecture. Before diving into the new engine, it helps to rewind back to 2019. At that time, Elon Musk expressed concern about the early Raptor program. He explained that the Merlin engine family, simpler than staged combustion engines like NASA's SSME or Russia's RD series, still held world records for thrust-to-weight and thrust-to-cost. Raptor had a higher specific impulse, but Musk worried it might fall behind Merlin on those two critical metrics. Merlin's design philosophy is all about simplicity and reliability. It uses a gas generator cycle in which a small portion of fuel and oxidizer burns inside a preburner to power the turbopumps. That exhaust is vented overboard, which wastes some energy but dramatically simplifies the engine. Lower pressures, fewer moving parts, and easier manufacturing make Merlin lighter, cheaper, and extremely reliable. And despite that simplicity, Merlin is a powerhouse, leading the industry in both thrust-to-weight and thrust per dollar. Because SpaceX mass-produces it efficiently, its cost-effectiveness remains unmatched. Raptor, however, operates in a very different league. It uses a full-flow staged combustion cycle, the most advanced rocket engine cycle ever developed, where all propellant runs through two pre-burners, one fuel-rich and one oxidizer-rich, before entering the main combustion chamber. This squeezes out maximum thermodynamic efficiency, giving Raptor a significantly higher specific impulse, but it also comes with huge engineering complexity. Earlier versions of Raptor were heavier, more expensive, and operated at far higher internal pressures, requiring advanced materials and intricate internal plumbing. That's what Musk meant when he worried Raptor might lag behind Merlin in thrust-to-weight and thrust-to-cost. Fast forward 6 years, and everything has changed. Musk recently announced that Raptor 3 will likely be 2 to 4 times better than Merlin in thrust per cost and will surpass Merlin in thrust-to-weight ratio. Even more exciting, Raptor 4 is expected to outperform Merlin by more than 10 times in thrust per cost, while further improving both TWR and specific impulse. That one update reveals 2 major breakthroughs: the arrival of the long-awaited Raptor 3 and the existence of a next-generation Raptor 4 that few people even knew SpaceX was developing. When Musk says Raptor 3 will be 2 to 4 times better per ton of thrust, he's referring to manufacturing cost efficiency, meaning Raptor 3 provides significantly more thrust for each dollar spent compared to Merlin, and surpassing Merlin in thrust-to-weight ratio is massive. Merlin 1D was the gold standard, but now Raptor 3 is expected to outperform it. Then comes Raptor 4, which takes everything even further with more efficiency, higher ISP, better vacuum performance, and dramatically lower cost per ton of thrust. Each new Raptor version is becoming cheaper, lighter, more powerful, and more efficient than today's best engines. Raptor 4 is not yet in production or flight testing, but Musk has already set ambitious performance goals. Vacuum-optimized variants could hit around 380 seconds of specific impulse thanks to larger expansion. Nozzles, Raptor 3 has already achieved a record-breaking chamber pressure of 350 bar, and Raptor 4 is expected to push even higher, extending SpaceX's lead in engine performance. The Raptor family has also been getting significantly lighter with each generation. Raptor 1 weighed about 2,000 kilograms, Raptor 2 dropped to 1,600 kilograms, and Raptor 4 is expected to land near 1,500 kilograms. Combine that with a massive 330 tons of thrust, and the result is a thrust-to-weight ratio around 220, well above Merlin 1D's 180. That difference is huge for reusable spacecraft. To achieve this level of performance, SpaceX is continuing its approach of pushing chamber pressures higher. Higher pressure increases thrust to weight, but also raises combustion temperatures, which can damage or melt engine components. To handle this, SpaceX is experimenting with advanced alloys, upgraded cooling systems, integrated cooling channels, and simplified internal plumbing. They'll likely retain Raptor 3's pipeless architecture, integrating plumbing directly into the engine walls to reduce mass and eliminate failure points. Elon has mentioned replacing the heavy bolted flange between the thrust chamber and hot gas manifold with a welded joint, which would save weight and improve reliability. Some might wonder whether SpaceX really needs engines this powerful. The answer is yes. Even though Starship is already enormous, Musk continues pushing for greater payload capacity to Mars, which demands more thrust inside SpaceX. There's a running joke. The Raptor team keeps increasing performance, while the Starship fuselage team keeps adding more dry mass. Cost reduction remains one of the biggest objectives for the Raptor program. Musk once mentioned his long-term target of getting the cost under $250,000 per engine. That's extremely ambitious, but not impossible. The raw materials alone, super alloys for the combustion chambers and nozzles, can cost nearly $100,000. Add sensors, electronics, and rigorous testing, and costs rise quickly. Automation will help, but mass production is the real key, just like with Merlin and Falcon 9. Raptor 4 is expected to feature more integrated components, fewer joints, and faster assembly. It will be built tougher and more reusable, designed to fly many times with minimal refurbishment. A realistic near-term cost for Raptor 4 is around $500,000, still an enormous improvement over earlier engines and a major step toward fully reusable, affordable spaceflight. The Raptor engine is central to SpaceX's entire vision. It's the first operational full-flow staged combustion engine running on liquid methane and liquid oxygen. Methane offers higher efficiency, cleaner combustion, longer engine life, and the ability to produce fuel on Mars using local CO2 and water Raptors are designed for rapid reusability with the long-term goal of thousands of flights per engine. They use 3D-printed components, custom alloys like SX500, and continuous design improvements to increase performance and simplify manufacturing. Each generation has improved thrust, ISP, thrust-to-weight ratio, durability, and manufacturability, supporting Starship missions such as orbital refueling, lunar landings, and Mars transport. Meanwhile, Rocket Lab's upcoming reusable rocket Neutron has slipped to 2026. CEO Peter Beck explained the delay during the company's Q3 earnings call, noting that more testing is needed before rollout. To launch Complex 3 at the Mid-Atlantic Regional Spaceport, Beck emphasized quality over speed, saying Rocket Lab won't rush to the pad or call a partial success good enough. Neutron is designed for recovery and reuse, but won't attempt a landing on its first flight. Rocket Lab is still preparing its 400-foot landing barge, return on investment for later missions. Beck also shared updates on their methane-fueled Archimedes engines, currently undergoing around-the-clock validation at NASA's Stennis Space Center. The engines are running 20 hours a day, 7 days a week, compressing years of qualification into months. As Beck put it, no weekends or evenings are being spared to finish testing.